When one polymorph turns into another, there are a couple of ways in which that transition can happen, and one of the ways is referred to as a reconstructive phase transformation. So what happens here, and another name for this, by the way, is also, it can also be referred to as a first order transformation, is that we're going to take the bonds and rip them apart. So this involves the breaking of atomic bonds as we rip apart one structure, and then we put things back together. As we put things back together, but in some new pattern. So we'll put things back together to make a pattern that has the same chemistry, of course, just as we discussed with polymorphs. We can have something, well, we'll just take the example here. We can have the element carbon. These are diagrams from the online textbook of mineralogy by Dexter Perkins. And in this case, on the left, we show carbon in the form of diamond. And on the right, we also have the very same element carbon, but here Mr. Perkins is showing it in the form of graphite. And to go from one phase to the other, if you want to be able to get from, let's say, this structure to this structure over here, or vice versa, then in either case, you're going to have to rip apart all these bonds. The red little circles here are the carbon atoms, and then these sticks are just showing the bonds that connect those atoms. Not really sticks, but it's just an easy way to illustrate it. So all those bonds are going to have to be broken apart and then rearranged to put into a new form. That new form here being these sheets that represent the structure of graphite. By the same token, if you want to get rich quick, you could take graphite from your pencil and compress it so it forms the diamond structure. And to do that, when you compress it, if you compress it at a great enough pressure, you're going to break apart all those bonds and then reform them into this structure here. So that's what we mean by reconstructive, or a so-called first order phase transition. These kinds of phase transitions have a certain number of, certain kind of properties. They tend to be slow. They're not easily accomplished. It's not easy to get from one structure into another, and they are not easily reversed. So that's supposed to be an N for not easily reversed. So once you make diamond from graphite, it's not so easy to go back and make the stuff you started with. Or by the same token, if you have diamond, if you have graphite and want to make diamond, it's not, once you make it, it's not going to snap back into the other structure. As we've talked about in some of our other diagrams, we can draw a Gibbs free energy diagram where we show, let's say, we'll put graphite over here and diamond over here at low pressures and low temperatures. Graphite is stable. It has the lowest Gibbs free energy, and diamond is not stable. But they're separated by a very large activation and energy barrier. And so if you've got diamond here, it is metastable. It's going to sit at this higher Gibbs free energy value perfectly happily without converting necessarily to this lower Gibbs free energy state, because it's stuck inside of this well. There's very large energy barrier here that prevents it from easily being transformed. Now you can transform it by heating it up, for example, but I have to put some action, put some energy into the system to make the reversal occur. And then finally, there's a distinct break in physical properties. So if we compare the hardness of graphite and diamond, well, they are on opposite ends of the spectrum. Graphite is very soft, diamond is the hardest known naturally occurring material. Now, we've used the example of diamond and graphite. We have this excellent diagram from Dexter Perkins. There are other examples. If we have the mineral cristobalite that has the formula SiO2, it could convert to, let's say, low quartz. That's the common kind of quartz that you might find in a granite. But it's not easy to get cristobalite to convert into low quartz. It is another example of reconstructive phase transformation, and some lava flows that precipitate SiO2 will form it in the cristobalite phase. And even though it's sitting at the surface at much colder temperatures, there's a high temperature form, it doesn't easily convert to that low quartz form because we need to break those bonds and rip them apart. It's very hard to do at low temperatures. Another example is aragonite and calcite. So a transformation from one or the other is going to involve tearing apart the atomic bonds and then putting them back together. So those are reconstructive phase transformations.